Alright, welcome back to the third video in this series in the scope of discrete mathematics. Once again, the purpose of this series is to teach you a introductory level, university level discrete math course. In the previous video, we covered logical operators and truth tables. If you missed it, on the top right corner, there's a link to the previous video. And you should also find a link to the entire discrete math playlist, which you could also find at the end of the video and in the description below. Alright, so before we start our quantifiers and nested quantifiers video, let's look at something we missed from the last video, which was De Morgan's law for logical operators. It's important to specify four logical operators, since there are several variations of De Morgan's law. Not all of them are for logical operators. Some of them we're going to see in this video. But yeah, basically, this is a conversion method from a conjunction to a disjunction, and it's very useful if you're taking a logic-based course or something like that. So basically what De Morgan's law for logical operators states is that if you have a statement not x or y, it is logically equivalent to the statement not x and not y. The three bars in this case, they represent logical equivalence, so it means whatever's on the right-hand side has the same truth table to whatever's on the left-hand side, right? So basically what this is saying is if you have a statement x or y, and if that statement is false, then both x and y have to be false, right? And logically that makes sense. If you have x or y and that's false, then neither x or y can be true. The second version of De Morgan's law for logical operators is the statement x or y is logically equivalent to not x and not y. So basically it says that if you have a statement x or y, that just means that x and y cannot both be false at the same time. So not x and not y cannot both be true at the same time, and and one of them has to be true at least in order to satisfy this logical expression. And I mean, that's logically pretty self-explanatory. So let's move on to quantifiers and nested quantifiers, which is the topic of this video. So what is a quantifier? Well, we've got two quantifiers which we'll cover in this course. The first one is the universal quantifier, which is the upside down A, and basically it means for all. So whenever you see an upside down A in proofs, problems, anywhere, you should be able to replace it with for all. It's basically just a short form for the statement for all. And then we have the backwards E, which is our existential quantifier. Existential quantifier. And it basically means there exists, right? So every time you see a backwards E in your proofs or problems, you can replace it with there exists. It's just a short form. Now, quantifiers, they have a significance in proofs because it's a shorthand way of writing for all and there exists, and we write those statements a lot of times in proofs. So it's important in this scope. Now in this chart right here, you'll see basically how to prove a statement which has the universal or existential quantifiers, and I'll switch markers so it's easier to see. But first let's look at what they mean. So if we have a statement right here for all x such that p of x, what does it mean? Well, if you remember from from the previous video, p of x essentially means it's a proposition, right? And this is a quantifier. So let's say in this case p of x means x lives in Paris, and in this case x is a person. Right, x is our argument and x is a person. So what does this statement mean? Well, this is short form. In long form, it means for all people x lives in Paris. So all people live in Paris. So this boils down to all people live in Paris. And then the existential quantifier in this case is the opposite. It says, not the opposite, but it's something else. It says there exists a person who lives in Paris. now from, common sense, we know that this first statement is false and the second statement is true, right? But it's not always that obvious when you get to mathematical problems. This is just, a basic example to, get you into the flow of things. But yeah, it's pretty obvious that this is false and this is true. But how would we prove something like that? Well, let's say we actually wanted to prove this statement to be true, right? Let's say we were on an alien planet, we knew nothing about Earth, and we wanted to prove this statement to be true. Now, in order to prove something to be true, it has to be true. If it's not true, we cannot prove it to be true at all, right? So, let's assume this is true for a sec. Let's assume that all people in the world just live in Paris and nobody lives outside of Paris. Well, how do we prove it? It's a very difficult process to prove it true, right? We have to begin the proof, end the proof. We have to write a whole formal proof, and we have to logically find a way to prove it, right? If you saw the proof by induction video, which was the first video in the series, maybe that might give you some ideas as to how to do it. But obviously, we'll cover this in future examples as well. But yeah, it would be difficult to prove since we would have to search every square inch of space outside of Paris to make sure that no other person lives outside of Paris. Now, how do we prove it false? Well, it's very easy. We just need one counterexample. And if you don't know, counterexample is basically a very strong example that alone falsifies an entire statement. So, if we wanted to prove this statement false, my bad, I'll finish my sentences before moving on. So, if we wanted to prove this statement to be false, we would just need to find a single person who doesn't live in Paris, and we could prove it false, right? So, very easy. Now, how do we prove this statement to be true? Well, there exists a person who lives in Paris. To prove it to be true, easy. Just look in Paris, find a single person who lives there, and boom, you've proven it to be true. Now, how do you prove it to be false? Well, again, that's way more difficult. Let's assume this was actually false. Let's assume nobody actually lived in Paris. You'd have to search every square inch of space in Paris to make sure not a single person lives there. So again, begin proof, end proof, and you have to write a formal proof in that sense. So a lot more difficult. Now let's move on to, a slightly more computer science based, a slightly more logic based example. So let's say we have a bag of apples. Capital B represents the bag, and a lowercase a represents apples, right? Or an apple, okay? And let's say we had a statement. We have a statement for all A. For all A that are elements of B, A is red. Also, this E looking placeholder means there exists, right? So we're gonna cover this in our set theory video. It's not up yet by the time of obviously posting this video, but if it is now, you're free to go and check it out. But yeah, it basically means that A is an element of B. So apples are in the bag; they're an element of the bag. So what does this statement mean? Well, it basically means that for all apples, for every apple in the bag, A is red. Maybe that statement is true. Maybe every apple that we put in the bag is red. Maybe that statement is false. Maybe we put some green apples in the bag too. So, again, that's just how you would read a statement like that. Now let's take the negation of that statement, right? Because again, we can apply logical operators to quantifiers as well. So let's take the negation of the statement. So what does this mean now? It means for all apples in the bag, the apples are red is false. That means not all apples in the bag are red. Again, this comes with practice, but if you think about it logically, if you do some practice questions, you can quickly determine how we can take complex sentences and boil them down to, make it a little bit more understandable. So yeah, again, this means that not all apples in the bag are red. But this is logically equivalent to saying there exists an apple in the bag such that the apple isn't red, right? So that means there exists an apple in the bag that is green. That's the only way a statement like this can be true. So that's why these two statements are logically equivalent. And that brings us to De Morgan's law for quantifiers. Remember, as I said, there's multiple variations of De Morgan's law. So now we're here at De Morgan's law for quantifiers. And in De Morgan's law for quantifiers, it basically says when you have a statement such that not for all A, such that P of A is the same as saying there exists an A, such that not P of A is true. Right. And the other variation of this, you can, logically, you can find the reasoning behind this as well. It's pretty self-explanatory. The other De Morgan's law for quantifiers is there does not exist an A such that P of A is true is the exact same as saying that for all A, P of A is false. Right? So if there doesn't exist a single A that proves P of A, that means that for every A, P of A is false. Again, pretty self-explanatory. But yeah, I guess now we can move on to nested quantifiers. So what are nested quantifiers? Again, I'll switch my marker. I think it's easier to see in white. But nested quantifiers are quantifiers inside quantifiers. So, if we have something like for all, now let's say we had multiple bags, right? So B referred to the multiple bags, and the S is important, and A represents the multiple apples. Again, the plural, it's important. So let's say we said something like this: for all B, there exists an A such that P of A. So that essentially says that for all bags, inside every bag, there's an A that satisfies P of A, right? We could also do something like, for all apples, there exists a bag such that P of A, right? So for every apple, there would exist a bag that proves P of A to be true. Now, there are some rules to nested quantifiers. We can't just, switch them around and make of them what we will. So saying something like this for all bags, that does not look good. All right, sorry about that. So we have for all apples, or for all bags, there exists an apple, such that P of A is true. That's not the same as saying there exists a bag such that for all apples inside the bag, P of A is true, right? So we can't just switch these and assume it to be true. That's not the same thing, right? However, we can switch these. So there exists a bag such that there exists an apple to prove P of A true. That is actually the same as saying there exists an apple such that there exists a bag which proves P of A to be true. These two are the same, and also it's the same with a universal quantifier. So for all B, for all A, P of A, same as saying for all A, for all B, P of A. And you can use examples to prove these statements, but yeah, all of them would prove true in all cases. So that brings us to the final thing we're covering, which is in this video, which is De Morgan's law for nested quantifiers. So the third and probably the final variation of De Morgan's law, which we will be looking at in this series, De Morgan's law for nested quantifiers basically says that the negation of there exists X for all Y such that P is logically equivalent to saying for all X there exists the Y such that not P, right? And then the second variation is for all X there exists a Y such that P, if that statement is false, then there exists an X for all Y such that P is false. Right. It's pretty self-explanatory. Again, these you can use examples to prove these. We will be using examples in future videos probably to prove these statements to be true. But yeah, that's basically the video about quantifiers and nested quantifiers. Again, thank you so much for watching this video. If you found this useful, please like, comment, and subscribe. And check out our playlist, which is probably you're seeing that on the screen right now, or you can find it down in the description below. Thank you so much. Bye bye.